Section 1. Cosmic Cradle, the Nebula. Space is not empty. It's filled with vast clouds of gas and dust called nebulae. These nebulae, often spanning light years across, are the birthplaces of stars. Imagine a swirling mass of hydrogen, helium, and heavier elements, remnants of past stellar explosions. These ingredients, scattered across the cosmos, hold the potential for new beginnings, for the creation of something spectacular. Within these cosmic clouds, gravity plays a constant game of push and pull. Every particle, every atom attracts every other. Over eons, denser regions within the nebula begin to coalesce. Like dust bunnies under a bed, these clumps grow larger, pulling in more and more material from their surroundings. This slow, inexorable dance of matter sets the stage for a star's grand entrance. As the clump grows, its gravitational pull intensifies, reeling in gas and dust at an increasing rate. The cloud's core, once a diffuse collection of particles, transforms into a dense, hot center. The temperature rises as the particles collide with increasing ferocity, converting their kinetic energy into heat. The once dark nebula begins to glow, a beacon of creation in the vast expanse of space. This is just the beginning. The journey from a nebula to a star is long and arduous, a testament to the universe's awe-inspiring power. As we delve deeper into this cosmic narrative, we'll witness the transformation from a cloud of dust and gas into a brilliant, shining star. It's a story of gravity, heat, and the fundamental forces that shape our cosmos. So let's continue our exploration into the heart of star formation. Section 2. Gravity's pull, the birth of a protostar. The dense, hot core of the collapsing nebula, now a swirling vortex of gas and dust, marks the birth of a protostar. This isn't yet a true star, not until it can sustain nuclear fusion in its core. But it's a crucial stage in the star's evolution, a period of intense heating and compression under the relentless force of gravity. As the protostar pulls in more material, its internal pressure and temperature continue to climb. The core becomes a chaotic dance of atoms, colliding and interacting with growing intensity. The protostar, though not yet shining with the light of fusion, emits infrared radiation, a testament to the immense heat generated by this gravitational contraction. This infrared glow can be detected by telescopes, offering a glimpse into these stellar nurseries. The protostar's evolution is a delicate balancing act. Gravity, the architect of this cosmic dance, relentlessly tries to compress the core. But as the core heats up, it pushes back, generating outward pressure that counteracts gravity's inward pull. This struggle between gravity and pressure determines the protostar's fate, shaping its future evolution. The protostar's path is not always smooth. Sometimes the infalling material forms a swirling disk around the central object. This disk, known as a protoplanetary disk, can eventually clump together to form planets, moons, and asteroids. So, in a sense, the birth of a star can also herald the formation of planetary systems, potentially harboring life-sustaining worlds. Section 3. Igniting the fire, nuclear fusion, and stellar stability. The protostar, a ball of superheated gas, continues to contract under its own gravity. The core temperature and pressure rise to unimaginable levels, reaching a critical threshold. At this point, the magic of nuclear fusion begins. Hydrogen atoms, the most abundant element in the universe, are forced together with such incredible force that they fuse, creating helium and releasing an immense amount of energy. This fusion process, the heart of a star's power, is a delicate dance of atomic nuclei. Normally, the positively charged nuclei repel each other, like magnets of the same pole. But in the extreme conditions of the stellar core, they overcome this repulsion, fusing together and releasing the energy that makes stars shine. This energy, in the form of light and heat, radiates outward from the core, finally allowing the star to shine brightly. The onset of nuclear fusion marks a turning point in the star's life. The outward pressure generated by fusion energy finally counterbalances the inward pull of gravity. The star achieves hydrostatic equilibrium, a state of balance that halts further gravitational collapse. The star is no longer a contracting protostar, it's a true star, shining brightly and steadily, powered by the nuclear furnace at its core. This delicate balance between gravity and fusion pressure defines the star's main sequence lifetime. For millions or even billions of years, the star will continue to fuse hydrogen into helium, radiating energy into space and illuminating the cosmos. This stable phase is the longest in a star's life, a testament to the power and efficiency of nuclear fusion. Section 4. A star is born, entering the main sequence. With the ignition of nuclear fusion, the star finally sheds its protostar status and joins the ranks of billions upon billions of stars in the main sequence. This is not just a change in nomenclature, it's a fundamental transformation. The star, once a contracting ball of gas, has found stability, a balance between gravity's relentless pull and the outward push of fusion energy. It's a cosmic balancing act, a testament to the laws of physics that govern the universe. The main sequence is not a static place. Stars evolve during this phase, albeit slowly. As the star fuses hydrogen in its core, it gradually depletes its fuel reserves. This depletion triggers subtle changes in the star's structure and luminosity. Over millions of years, the star may brighten slightly as it adjusts to the changing conditions in its core. The main sequence is the longest and most stable phase in a star's life. It's a time of stellar maturity, a period when the star shines steadily, providing light and heat to its corner of the universe. The duration of this phase depends on the star's mass. Massive stars, burning brightly and furiously, have shorter main sequence lifetimes than their smaller, cooler counterparts. The entry into the main sequence marks the end of the star's birth and the beginning of its adulthood. From its humble beginnings in a cosmic cloud of gas and dust, the star has ignited its internal furnace, achieving a state of stellar equilibrium. It now shines brightly, a testament to the awe-inspiring power of gravity and nuclear fusion, illuminating the vast expanse of the cosmos.